Hey guys, this is lesson 13.2. What does it mean for light to be quantized? Before we talk about quantization of light, we have to talk about black body radiation. Black body radiation was studied in the early 1900s by Max Planck. A black body is an object that is a perfect absorber of energy. That means if we were to shine, let's say, white light on it, all the colors of the light would be absorbed by that object and it would appear black to your eye. That object would then heat up and also emit energy. So perfect absorbers are also perfect emitters of energy. While there are no real perfect black bodies, many objects can be approximated as black bodies. So at room temperature, a black body appears to be black. But if we were to heat up that object, as it heats up, it starts to glow. And it'll start to glow red, and as it gets hotter, it'll glow white. As it gets even hotter, it could even glow blue. So looking at the picture, you can see that the end of the metal bar closest to us is black. It definitely looks like the coolest part, whereas the other end is glowing white. We can tell that's the hottest part. This diagram shows the wavelengths given off by a heated black body. We can see that if a black body is heated to 3000 Kelvin, that it gives off a wavelength of about 1.2 micrometers. This is not visible, but if that black body were heated, when it got to about 5000, the peak wavelength that it gives off is about 700 nanometers, and that is visible. That is red light. This would be an object that is red hot. If we continue to heat that black body, when it got to 6000 Kelvin, you can see the peak wavelength it gives off is in the yellow part of the spectrum, but it also gives off plenty of green, blue, and violet, orange, and red, and so that mix of colors appears to be white. And so by looking at a black body and seeing what color light it's giving off, or what wavelengths of light it's giving off, we can estimate the temperature of that black body. The sun, for example, is pretty closely approximated by being a black body, and our sun is a very white star. And so you can approximate the temperature of the sun to be about 6000 Kelvin. And in fact, when you look it up on Wikipedia, it tells us the surface temperature of our sun is 5778 Kelvin. Here's a thermal image of a person. The person is not hot enough to be giving off these colors of light, this white and this blue, but what's actually happening here is the person is hot enough to give off infrared wavelengths of light. And there's a camera that can receive those infrared wavelengths of light, and it then changes those or shifts those up to visible light frequencies and wavelengths that we can see. So we can see from the black body experiments that the hotter the object is, the more energy its molecules have, the higher the frequency and the lower the wavelength of the light it emits. In fact, light, when emitted, is emitted in photons, packets of light. And we can use this formula to calculate the energy in one of those single photons of light. This letter here, H, stands for Planck's constant. It's 6.63 times 10 to the negative 34 joule seconds, and that can be found on the front of your reference table. You can see that the higher the energy, the higher the frequency of that photon. Now, we're talking about light here, and we can use the wave speed equation to figure out how frequency and wavelength are related. And all of these experiments are occurring in vacuum or in air, where light travels at c, 3 times 10 to the 8 meters per second. So I can solve this equation for frequency. And I can plug in for F, I can plug in c over lambda, and I get the relationship between wavelength and energy. The greater the wavelength, the less the energy, or the smaller the wavelength, the greater the energy carried by that photon of light. So the total energy emitted by a monochromatic light source must be a multiple of the energy of a photon of the emitted frequency. What this means is a monochromatic light source, a light source that's giving off only one frequency of light. If we were to collect the energy given off by that light source, the total amount of energy must be a multiple of HF, because HF is the energy of a single photon, and we always must get a whole number of photons. There are no fractional photons. This is sort of like the principle we had when we talked about electric charge, and all charges must be a multiple of the elementary charge. When we calculate the energy of a photon, it usually turns out to be a very small number of joules. To make this number more meaningful and easier to relate to other people, we've invented a new unit called the electron volt. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So we'll use this as a factor and use factor label to convert between joules and electron volts. So let's summarize what we know about a photon. If we knew the wavelength of a photon, we could find its frequency. Or if we knew the frequency of a photon, we could find its wavelength using the formula V equals F lambda, knowing that V is the speed of light, 3 times 10 to the 8 meters per second if we're working in vacuum or if we're working in air. And we can take that frequency and we can look it up on the reference table and figure out what color light that is. In this lesson, we learned that you can use the formula E equals HF to figure out how much energy is carried by a photon of a given frequency, or we can use E equals hc over lambda to figure out the energy from the wavelength. Remember, h is Planck's constant and can be found on the reference table. It's equal to 6.63 times 10 to the negative 34 joule seconds. Once we have our energy in joules, which usually is a very small number for photons, we may want to convert it to electron volts to be a more manageable number, and we'll use factor label and the conversion factor 1 electron volt equals 1.6 times 10 to the negative 19 joules. So let's try some problems. My suggestion is that you pause the video, read the question and try it on your own, and then hit play and see if you got the right answer. So the first thing we want to do is find the wavelength of this photon. And we know the frequency, so we can do V equals F lambda. The speed is 3 times 10 to the 8 meters per second. The frequency is 4.5 times 10 to the 14 hertz. And we're looking for the wavelength. And so when you take 3 times 10 to the 8 and divide it by 4.5 times 10 to the 14, you get a wavelength of 6.7 times 10 to the negative 7 meters. Next, we want to find the energy of this photon. And so I'll use the formula E equals HF since we were given the frequency in the problem. If you wanted to do E equals hc over lambda, that would be okay too. Remember, h off our reference table is 6.63 times 10 to the negative 34 joule seconds, and the frequency is 4.5 times 10 to the 14 hertz. And so our energy turns out to be 3.0 times 10 to the negative 19 joules. For part C, we want to convert this into electron volts. So 3.0 times 10 to the negative 19 joules. We'll set up our factor. I like to put the units in first, so we want the joules to cancel out, so I put joules in the bottom and electron volts on the top. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And when I calculate this, 3 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19, I get 1.9 electron volts. In example 2, we have a photon of 3 electron volts, and we want to convert this into energy in joules first. So I'll use factor label. One electron volt will go on the bottom, so the electron volts cancel. And on top, I have 1.6 times 10 to the negative 19 joules. And so this would be 4.8 times 10 to the negative 19 joules. Next, I'd like to find the wavelength, so I'll use E equals hc over lambda. You can plug in the numbers or you can rearrange it first. So I'm going to get the lambda by itself, and that will equal to hc over E. I think it's easier to move around the letters in this case because the numbers are so big. 6.63 times 10 to the negative 34 joule seconds for Planck's constant. 3 times 10 to the 8 meters per second for the speed of light in vacuum. And the energy, we're always going to use joules in these formulas. 4.8 times 10 to the negative 19 joules. And so our wavelength turns out to be 4.1 times 10 to the negative 7 meters. Now we want to find the frequency. So we can use E equals HF. We also could have used V equals F lambda now that we know the wavelength. I'll rearrange the letters first. So F is equal to E divided by H. The energy was 4.8 times 10 to the negative 19 joules. And Planck's constant, 6.63 times 10 to the negative 34 joule seconds. And I get 7.2 times 10 to the 14 hertz. The last thing we want to know is what color or type of photon this is. When I mean type, I mean it could be infrared or ultraviolet. But when we look this up on the reference table, we can see that this frequency turns out to be in the violet part of the spectrum. In this example, I want you to find the range of frequencies, wavelengths, energies in joules, and energies in electron volts that comprise green light. You'll find the answers on the next slide. Using the reference tables, we can look up that the smallest wavelength that's considered to be green is 5.20 times 10 to the 14 hertz. And the largest frequency that's considered to be green is 6.10 times 10 to the 14 hertz. Converting this to wavelength using the formula V equals F lambda, where V is the speed of light, 3 times 10 to the 8 meters per second, we get a wavelength range with the smallest wavelength being 4.92 times 10 to the negative 7 meters, and the largest wavelength being 5.77 times 10 to the negative 7 meters. To get the energy, you can use E equals HF or E equals HC over lambda. The smallest amount of energy that was green is 3.45 times 10 to the negative 19 joules, and the largest is 4.04 times 10 to the negative 19 joules. Now to convert this to electron volts, we use factor label, where 1 electron volt equals 1.6 times 10 to the negative 19 joules. The smallest amount of energy is 2.15 electron volts, and the largest amount of energy that's green is 2.53 electron volts. In this problem, we have a monochromatic source that's emitting light with frequency of 5.6 times 10 to the 14 hertz. To figure out the energy here, we'll do E equals HF, and that's giving us the energy of each photon that's emitted. So we'll multiply H times the frequency, and we find out that each photon has an energy of 3.71 times 10 to the negative 19 joules. We can convert that to electron volts with our factor label. 1.6 times 10 to the negative 19 joules is 1 electron volt. And we find out that each of these photons has 2.32 electron volts of energy. C seems to be a tricky one. How many photons hit the detector? Well, it's telling us that a total of 18.56 electron volts hit the detector. And we know that each photon is 2.32 electron volts. Put this in your calculator, you get 8 photons. Now we knew this had to be a whole number because light is quantized. So even if you get a fraction that's close to 8 on your calculator, you don't want to write that fraction or that decimal. You want to give us a whole number of photons.